Our guest speaker tonight is Dr. Uwe Trittmann. He's professor of physics at Otterbein University in Westerville, and he's the director of the Wettkamp Observatory at Otterbein, and is the author of Constructing the Expanding Universe. Also, he presents a series called Starry Monday, which is a series of presentations at Otterbein held the first Monday of each month while classes are in session. And what they usually do, I up until the COVID hit, I was going to this regular, and it was really kind of nice because when his lecture was over, then we would go up to the top of the science building where they have the observatory and do some observing. But that's pretty much gone now. So, last but not least, he is a member of CAS. Okay, and tonight his presentation is a cosmic ladder of distance, measuring the distance of objects in space. So without further ado, I'm pleased to announce or to introduce Dr. Uwe Trittmann.
Well, thanks for having me. Let me share my screen here. All right, and I'll start from the beginning. Yeah, as Jim said, we have our Starry Mondays at Otterbein. That's where I hail from. And we actually still going. So we just had one and in person. So we're doing it by sign up, and the numbers are pretty small anyways. Yeah, we actually even got some observing in on Monday, whenever that was, 7th, I think. So we saw the moon. We just lucked out because we have usually a lecture first, and then the observing at 8 o'clock. And it just so happened that it was still clear at 8 o'clock. And when I, sat in the car half an hour later or something, it was clouded over. Then it became clear again, but we lucked out for that at least. So a couple of students there. So it was good. All right, so the talk about the cosmic distance ladder, let me know if you have any questions during the talk, after the talk, everything's fine. Hopefully somebody will notice if somebody, raises the hand or does something to get my attention, and I'll be glad to stop anytime. All right, so let's get started. The astronomical distances, and I'm of course telling a lot of you guys nothing new here, but the two of the three coordinates that we measure for a three-dimensional space are very easy to measure, right? The two angles, which you can of course do in a couple of different coordinate systems, but it's an angle that basically goes up down and an angle that goes left right. The idea is, of course, that the sky is something two-dimensional. But if we want to know something about the universe, then we really need the third dimension. We need the distance to the objects, and that turns out, as you all know, to be a pretty complicated story. And actually, for humankind, I'm teaching this astronomy general ed class at Otterbein, where we put emphasis on this the whole story of like, how did we come to know the expanding universe, right? Constructing the Expanding Universe. That's the title of my book too. So this is actually a pretty interesting, pretty long story, right? Now the problem is, of course, that angles don't tell us the whole story. So something could be close to us and small, or it could be a really big object but far away from us, and they would all both appear under the same angle. The prime example there is the sun and the moon, right? They exactly have the same angular size, about 30 arc minutes or half a degree when we view them from the Earth. And so it could be that they're the same size, but then they would have to be at the same distance. And of course, we immediately know from solar eclipses that the moon must be closer to us because the moon eclipses the sun and not the other way around, right? So the sun is actually farther away. That was pretty clear for since thousands of years. The question was, how far away is the sun, and in particular, how much farther away is it than the moon, and that means how much bigger is it than the moon. So that was early on a big question that could not be answered. And in fact, even Isaac Newton in his famous book in the 1600s, I guess, late 1600s, was still using the value that was obtained by the Greeks, which was just an estimate. And we'll get to this. So on Earth, of course, we have no problem with that because we know how big objects are, like a horse and trees and a church maybe. And if a artist depicts these in a picture, then, painting the horse really big, that just suggests to us that the horse is much closer than the other objects because we know their actual size, right? In astronomy, of course, we have no idea how big objects really are. At least initially not, right? So for instance, galaxies are just nebulous blobs. And so there could be, something else, and some others are actually other things, right? Like globular star clusters, for instance, are not galaxies, but they look kind of the same. So until you know their distance, you don't really know the true nature of these objects. All right, so the other problem that we have is that the universe is organized in very different length scales, right? We have some things that are very close to us, the solar system, right? Our fellow planets, they are fairly close. And then we have other things that are pretty far away and other things that are very, very far away. And as we do on Earth already, we measure distances of the human scale with the yardstick, which is convenient, but that already on the geographical scale is not convenient anymore, right? Because we don't have that many yardsticks around to measure the distance, for instance, between cities even. So we use triangulation there, and I'll get to this, how we do this. Of course, most of you will be familiar with that. And then these days, the solar system scale can be measured very precisely with radar ranging, sending a radar signal pinging off something and then measuring how long it takes to come back. And we know radar travels at the speed of light, and so therefore that is a very simple thing to do. If you're in close range, close as in like next planets, so to speak. And then we have to go further out with other methods. The stellar parallax was the first method that was used to get finally, after thousands of years, the distance to the stars, to positively measure the distance to stars. In 1838, that was done by Bessel. And then later on, as we understood more about stars, we can actually use that knowledge, and that then repeats itself. Basically, you gain knowledge by knowing the distance to some objects that are fairly far away. And then knowing the true nature of these objects, you can use that knowledge to get another step into your ladder, another rung in your ladder, and work your way up all the way to the end of the observable universe. So that's the idea. There's a couple of names, but we'll hopefully get through all of them. So here's the parallax effect, right? So if you're not familiar with that, then just do the quick demo here with your thumb and your eye. So if you close one eye and look at your thumb, and then close the other eye, then your thumb is jumping in front of the background in which it appears. And if that thumb is closer to you, it will actually jump more. And if it's farther away, it will jump less, right? So that's the parallactic effect in a nutshell. So that means that by looking at an object from two different vantage points, let's say viewpoint A and viewpoint B, you can actually triangulate the distance, because the background change, so to speak, will tell you how far away this object is. If there's a lot of background change, if that object really appears in front of a very different background, then that object must be very close to you, because if it's very far away from you, then you would hardly notice any difference between the two viewpoints, right? The other thing, of course, to keep in mind, that these viewpoints should be, as far away from each other as possible. And initially, of course, there was not a lot we could do there until we figured out the size of our planet. Then we could use our own planet 12 hours later. We're turned to the other side. So we have two viewpoints that are 1 Earth diameter apart. or later on, when we were able to figure out the size of the Earth orbit, we could use the Earth orbit as our baseline. And then, of course, we have two astronomical units, or about 300 million kilometers, or about 180 million miles, and that is quite something. But as it turns out, to measure the distances to stars, that's still a very, very small baseline. All right, so here's the idea. Here's two suggestions. One is the overlay of the image of the moon as it would be seen from different vantage points on Earth. So we're using the Earth here as the baseline, and if you would observe the moon from the South Pole, it would appear here, from the North Pole here. So that's the parallactic difference, or from the equator at 180 degrees different longitude. So you could see that, you could really see the moon move. It would appear, here's the Pleiades open star cluster as a scale factor, so to speak, so that the moon actually does move by about 2 degrees or so. 1 degree as the really the parallax angle, but the movement is 2 times the parallax angle, so about 2 degrees. And if you actually put this in the formula and saying, okay, if the baseline is really the diameter of the Earth, you can get pretty close to the distance to the moon. This was actually done in the 1700s by 2 French astronomers, one from Berlin in Germany and the other one from Cape Town, and they happen to be about 90 degrees apart in latitude. They're almost the same longitude, so that was a very easy, very easy calculation, not a very easy measurement, because back in the 1700s was quite a bit to get to Cape Town, right? You had to sail to Cape Town and so on. So for the stars, as I mentioned already, we would do the Earth motion around the sun, and then triangulate this near star. I think I also mentioned that the parallax angle is just half the angle there, right? You observe the movement 1/2 year apart, or 6 months apart, but the parallax angle, because you need a right triangle, is only half that angle. Now, of course, if you wait 6 months, the bigger the angle is, the better the chances are to observe that. And again, this was not observed until 1838, right? So it's very late in the game. Telescopes had been around for 100 to 200 years at that point, but they were not precise enough to actually do the measurement. All right, but where we have to start really is here on Earth, right? So the first thing that we need to know is how big is the Earth before we can leverage that as a baseline to triangulate things that are off the Earth. So really, truly astronomical objects, right? The measurement of the Earth was done by the old Greeks. Eratosthenes did this about 300 years before our time, and he used the fact that sunlight is on one particular day, actually on the summer solstice, June 21st, is right overhead in a city called Zain, and I'm not sure if I really pronounced that correctly, in Upper Egypt. And it is not at the same time overhead, but about 7 degrees off, being overhead in Alexandria. And that, if you think about this, here's a little insert. That means that really this 7 degrees here represents the difference between the 2 cities, the angular difference between the 2 cities. And if you measure the distance between the 2 cities, then you can actually, then this is 7 degrees, then you can actually scale this up, right? You can actually figure out the circumference of the Earth. And with that, you can get the radius of the Earth, right? So the angle measured here is about 7.2 degrees, which happens to be about a 50th of 360 degrees. And therefore, the distance between the 2 cities must be 1/50th of the Earth's circumference, right? So it's a very simple measurement. Of course, measuring cities different distances between cities was probably not all that accurate in the days, but oh well. The measurement came out to be about 7% off. 7 seems to be the lucky number here, right? Everything is 7 here, the angle and then the percentage off. So that was a very good measurement, and that has been used pretty much in really the millennia afterwards as the value for the radius, for the circumference, and therefore the radius of the Earth. Next thing, of course, would be moon, right? That's the next door neighbor. And so how do we get the distance to the moon? Here again, the Greeks thought of a very clever method using basically triangles that can be gotten by special configurations between the moon and the Earth and its shadow. So the question is basically, how big is the shadow that the Earth casts at the distance of the moon? Okay, here's a little animation. These are a couple of pictures that I took myself, so not very good pictures, but oh well, just snapshots through a 8-inch telescope or so. This is a lunar eclipse as it's progressing. And so if you want to just get a rough idea how this works, then the shadow of the Earth would be curved on the moon because it's really a disk. So here's that rough size of the disk. And then you could say, let's just make a circle around the moon. We know the moon's diameter there. And the question is, how many times does the moon diameter fit in the Earth shadow, right? So this is about 3 times or so. And if you're a little bit skeptical about my my method here, then let's just take a good photo from NASA. And of course, you guys probably did. Some of you at least did something very similar. So just and the moon, as this progresses through a partial lunar eclipse, here you can see very well that this shadow of the Earth is indeed a very nice round disk. And again, you take a circle of the moon and then fit it in, and again you get roughly 3 times, right? So that's how the old Greeks did it. They determined that the size of the Earth's shadow is about 3 lunar diameters, and then you can do some somewhat fancy geometry, where we compare triangles and so on, and you actually get the distance to the moon fairly precisely, right? If you have the distance to the moon, then you also know how big the moon is, because you then know the radius of the orbit, and you know that the moon is actually occupying only 1/2 degree. I already mentioned this, right? The 30 arc minutes of these 360 degrees that the moon's orbit would be. And then the moon comes out to have a diameter of about 3,350 kilometers. Okay, so that's the idea. Next one is the sun, and that is actually not a success story initially, because the sun is very far away. As it turns out, the sun is about 400 times further away than the moon, and therefore 400 times bigger than the moon, because they both appear at the same size to us on Earth. And that was just a little bit too far away for the Greeks, because, as you know, they didn't have any telescopes. So, angular measurements could not be made very accurately. They had a very nice idea there for a measurement. And the idea was to observe the 3rd quarter and 1st quarter moon. And they would be slightly off, being 180 degrees from each other, if the sun is fairly close to us, right? If the sun's close, what you need for a quarter moon is, of course, that the moon, the Earth, and the sun would be at 90-degree angles. And that means that if the sun's very close, you have to kind of shift the moon towards the sun a little bit. So they're not quite 180 degrees apart from each other, right? As it turns out, the sun is very far away, about 400 times the distance to the moon. And so therefore that difference is only about 1/6 of the degree. And that's not something that the old Greeks could measure. Okay, so they could come up with a limit which said the sun has to be at least as far away as that, and they came up with about 20 times. So they were actually 20 times short, right? And that very, very close distance to the sun was actually even used about, well, I guess 2000 years later by Isaac Newton. Luckily with not a lot of fallout, basically. So he didn't really conclude anything wrong about the laws of gravity or something like that. Okay, so you might think that with progress in astronomy, you would get this somehow, clever methods to figure out what are the sizes of the orbits of the planets. And there is Kepler's third law, which relates the orbit sizes. As you know, the period squared is proportional to the semi-major axis A cubed. And so you might say, okay, there we go. We have the orbit sizes of the planets. For instance, Jupiter's orbit is about 5 times bigger, 5 cubed, divided by 12 years, and it takes roughly to go once around the sun, is roughly 1, right? So if we just round everything to integers. That unfortunately doesn't work because these are only relative sizes, right? So the Earth distance from the sun comes out to be 1, but the question is, how big is 1, right? What is 1? In what units? And of course, in astronomical units, but the astronomical unit, unfortunately, is just defined as the distance Earth-Sun, and that means you don't really know it, right? You just give it a name. And so therefore, that method doesn't work, right? You need to actually know at least one distance of one planet from the sun, or maybe the distance between 2 planets, and then you could actually do this. So how can we do this measurement? And there's a couple of, well, really 2 different ways to go, right? Either you're related to a distance on Earth that you know, and so you project that out to the solar system, or you take some process that you know from the lab, a constant of nature, and use that, right? The constant of nature, of course, that I'm talking about here is the speed of light. And if you know what the speed of light is, and you measure how long a signal takes to go to, let's say, Venus and bounce off there and come back, and is measured, then you've actually measured the distance to Venus, really 2 times the distance to Venus, and therefore you can scale it up, and you can get the astronomical unit. Now, of course, this method was not available until the 1960s or so. Actually, the laser was invented in 1960. Before that, there's a very interesting story about measuring this distance, the astronomical unit, the distance really to Venus, by Venus transits. If Venus transits in front of the sun, it turns out that depending on where you are on Earth, it looks a little bit different, right? So let's take a look at this. So the Venus transits, here's a little animation. So Venus appears as a very small dot, almost like a sunspot that goes in front of the sun. Unfortunately, these events, the Venus transits, are very, very rare, right? There's pairs of 2 transits that are apart roughly 110, 120 years or so. So roughly once a century, you would get a Venus transit, right? So you want to make sure that you don't screw anything up, and you have, everybody in lots of different locations, very far away from each other. And, if the weather's bad in one location, then hopefully you have another one that measures it from another location, right? And if you do screw things up, you get a second chance about 8 years later. Okay, so let's take a look at why this would work. So here's the sketch. If you have the sun here and the Earth here, and in between you have Venus, just this dot here. So it's not to scale, and you observe from 2 different points on Earth, then you would actually see Venus do slightly different things, right? So from one vantage point, it would look like Venus is lower on the sun, transits lower, and then from another vantage point, it would be higher, right? And what you want to do is measure the difference, basically, and then somehow with a calculation, translate that into a distance where Venus is, and your baseline would be, again, of this triangulation would be the difference location on the Earth, right? The distance between the 2 points. All right, so here's how this works. This is a transit of Venus. We have these 4 contacts. Contact 1 would be where Venus just so is about to enter the face of the sun. And number 2 is where it just so gets away from the edge. And then we have 3 where it touches the edge of the sun, limb of the sun again. And 4 is when it's completely out, right? And so in principle, that might look like, okay, black dot in front of the sun, get your solar filter on, just, set your clocks right, synchronize your clocks, which of course back in the 1700s was a little bit of a problem because good clocks were not around. They actually tried to make as good clocks as possible, but you had to have a clock, pendulum clock or something that was stationary. So pendulum clocks do not work on ships, for instance. So you can't just take a ship, go in the middle of the ocean. That wouldn't work. You have to be somewhere. So here's actually a little photo series that we took back in 2004, and you might know that this was the year of the Venus transit, one of the years. There was another one 8 years later, 2012. As it turns out, 2004, we had super weather. We observed at Prairie Oak Metro Park. So here's 2 Celestron 8 telescopes, one with a solar filter. This is actually Dr. Robertson, also from the Otterbein Physics Department. And we had news coverage and everything. It was, really pretty much perfect. It was like early in the morning, 5:30 a.m. Sun was just coming up. Venus transit was already going on. And weather was just, perfect, as I said. So we did a couple of things, projection on paper, and then of course the solar filter. And this is where these photos come from that I'm showing you here. This is, you can see just a snapshot through the Celestron 8-inch, at probably like 50 times magnification. Here's a little dot. No sunspots around actually, so it's very clear to see, right? So that's good. But if you look closely, this is contact here, contact I guess between 3 and 4. So Venus is leaving the sun, but as you can see here, there's of course something going on with the optics here. Clearly some discoloring. The other thing you could see is this black drop effect that was noticed for the first time at the first professional Venus transit observation in the late 1700s, that unexpectedly Venus, when it gets close to the limb of the sun, will look like a little tar drop or something. And so it will not be very easy to judge exactly when does Venus touch the limb of the sun. And that is, of course, that back in those days, that was pretty much catastrophic, unanticipated. And it turns out to be an optical effect that, you just can't work around. Has nothing to do with the optics or anything like that. So there's nothing you can improve there. The other thing that you might see here a little bit is this, and of course I'm cranking up brightness and contrast and so on into things that I should probably be doing, but you see a little bit of the atmosphere of Venus here, right? You see that little bit brighter rim here of Venus. So this is the atmosphere of Venus scattering light to the dark side, and you can really see that Venus must have an atmosphere. That was actually observed by Lomonosov back in the 1700s. So Venus was the first known planet to have an atmosphere since the I think he did this in the 1760s. All right, so that's the Venus transit, which then gave a reasonable estimate of the astronomical unit. And once you had that, then you're good to go out to the stars, right? Because then you have the baseline. Your baseline now can be as big as the orbit of the Earth, where you're just flying to the other side by just waiting 6 months and observing whether a star that you suspect is fairly close to you will change or will move in front of the background, right? And if you think about this, then, in hindsight, that's pretty, straightforward to do, right? But the question was, which ones are the near stars, right? There's lots of stars, and most stars are way too far away to show any parallax movement. In fact, until the 1830s, all stars had been too far away to show any parallax, right? So people had been trying to measure the parallax, and you might know the story of the stellar aberration that was found much earlier, and is a much bigger effect, where Bradley actually suspected that he had found the stellar parallax, but as it turns out, he had found the stellar aberration, which is the effect of the finite light speed, and is, as I said, a much bigger effect. All right, so here the idea is, as I said, to measure the parallactic angle, the half the change that a star would do, the angular movement of a star in half a year, and then do the math of a right triangle where you know one of the sides of the triangle, you know two of the angles, the 90-degree angle, of course, and then the parallactic angle that you just measured. And it's convenient to use that as a distance unit. So this is where the parsec comes from. If you ever wondered, that's the parallactic second, right? So it's a distance in parsec would be, if you measure it in parsec, it's a very easy calculation there. So 1 divided by the parallactic angle in arc second is the distance in parsecs, right? So a star with a movement of 2 arc seconds, meaning having a parallactic angle of 1 arc second, is 1 parsec away, 1 parallactic second away, and that is about 3 light years or so. Okay, so once we do that, then we notice that actually some stars are fairly close to us, about 4 light years or so, and some other stars, bright stars that we can see in the night sky are actually like 1,000 light years away, right? So that immediately showed astronomers that some stars would appear dim, but are actually very bright, right? So if you have a star that's 1,000 light years away and it appears, fairly bright, they must be really, really very luminous, as we say. Okay. Okay, so here's just a map, a 3-dimensional map now of our solar neighborhood, of our galactic neighborhood. And if you look at the star names here, you'll notice that most of them are very obscure, right? They typically just have numbers in a catalog. The only stars that we know from the night sky are Sirius here and Procyon, and 61 Cygni, which is actually the first star that was measured, had a parallax. And then we, of course, have Alpha Centauri, the closest star to us. Actually, it's Proxima Centauri, but that's part of the Alpha Centauri system. And you can understand now why Sirius is the brightest fixed star. It is so bright because it is very, very close to us, right? It is about 25 times as luminous as the sun. So it is also very intrinsically very bright, but it's also very close to us, right? Okay, let's see. I don't know, are there any questions so far? Oh yeah, okay, so, okay, good. All right, great. Just comments, I guess, in the chat. Okay. So the next thing, or for the really remaining, all the remaining methods to measure distance, we need to understand the difference between luminosity and brightness, right? Luminosity and brightness are sometimes used interchangeably, but they shouldn't really. The brightness is the appearance, right? How bright something appears depends on 2 things. How bright is it intrinsically, and that is called luminosity, and how far away is it, right? So it's really depending on the observer, right? Different observers would observe different brightnesses because they probably have different distances from the object. So luminosity is something like the wattage of a light bulb. So a 100-watt light bulb would send out a certain amount of light or a certain energy, and that is the luminosity. So that's really something that tells us something about the light bulb, right? Not about the observer, but about the light bulb itself. So this is really very useful if you want to understand and compare stars. you want to talk about luminosity. The brightness, the apparent brightness, is something that is readily observable in the night sky. You could just see how bright does a star appear, right? And the two are related by the distance, actually the distance squared. The basic idea is that, as you can see here in this little cartoon, the light source would send out light, and that light would dilute as it will go into the distance and will go away from the light source, and it will actually spread out over a sphere, over the surface of the sphere. So the intensity of the light, the brightness, would actually go down like the radius of that sphere squared, because that is how areas are computed, right? So the sphere has an area that is proportional to the radius squared. That's where that 1 over the distance squared comes from that area idea. So if it spreads out over a sphere that is twice as large, then really it spreads out over an area that is 4 times as large, or 2 squared. And then if it's 3 times farther away, you actually would have to cover 9 squares with the same amount of energy. And so that means that the intensity goes down by 9, right? Okay, so hopefully that was clear. If you think about this in terms of light bulbs, a 100-watt light bulb is very bright if you're pretty close to it, but it would be 9 times dimmer from 3 meters than from 1 meter away. 25-watt light bulb will, of course, look 4 times dimmer if at the same distance of the 100-watt light bulb, because it is 4 times dimmer. Really, it sends out 4 times less energy. And if they appear equally bright, but one is a 25-watt light bulb and the other one is a 100-watt light bulb, then of course well, not of course, but then you can compute that the 100-watt light bulb must be twice as far away, right? It's 4 times, factor 4 there in luminosity, but then it goes with the square of the distance. So it's actually only twice as far away. And that means it appears 4 times dimmer. So that means it appears as dim as the 25-watt light bulb. As you can see, this is a little bit dated because light bulbs these days are not measured in watts anymore, right? They're lumens output and so on. So this is back in the good old incandescent light bulb days. So if you do the same thing with stars, and here's a little bit of extra that we'll get to, then you want to compare stars that have the same luminosity, right? How do you know that? And as we'll see in a slide or so, you can judge this fairly easily from the color of the star, right? The color will give away, typically, if you're not too unlucky, what the temperature of the star is on the surface. And that will give away how much energy it puts out, basically. So if you look at 2 white stars like Sirius and Vega, they appear, they are as bright. One is as bright as the other because they're both white, right? So white stars would have a certain luminosity. You don't know what it is, but you know it's the same for these 2 stars. Then it turns out that if you look in the night sky, Vega appears about 9 times dimmer. So that means that Vega must be about 3 times farther away. And if you look up the numbers roughly, you would find indeed that Sirius is about 9 light years and Vega is 27 light years away. Okay, so that's the idea. If you know the luminosity, and there's a big if here, of course, then you can look up in the night sky and determine the brightness, and the ratio of the 2 will give you the distance, right? So the distance actually is the square root of the luminosity divided by the brightness. So that's the brightness luminosity distance relationship, as it's sometimes called. All right, so on we go with understanding objects. If you understand objects, you understand how luminous they are. If you know how luminous they are, then you can check how bright they appear, and then you can judge how far away they are, right? So that's a very nice way, and it takes you actually a very long way into the universe. So the stars, as we observe them, have actually different colors, and it was found out after a couple of decades, I guess it took, that these colors are proxies for their temperature. All right, so the blue stars are the hottest. They're the so-called O stars, about 30,000 or so Kelvin. And then the M stars are the coolest, about 3,000 Kelvin, so only a factor of 10 there, but they appear red. And so roughly, you could say, well, if I can see the color of the star, really, you would, of course, probably take a spectrum of the star and so on, but let's just simplify things. Then you could tell the temperature, and then the temperature would set, you could calculate this, you could do some physics maybe, and use the Stefan Boltzmann law, for instance, that says that the power output of an object is proportional to the temperature to the fourth power, right? So you get a very good idea of how much energy the object puts out, really how much power it puts out, and that is pretty much the luminosity of the object, right? Okay, so it turns out that here's another nice fact about stars, which you probably know, is that most stars will be so-called main sequence stars, normal stars, that are in a basically diagonal on this so-called Hertzsprung-Russell diagram. A Hertzsprung-Russell diagram is a diagram where you plot the luminosity of a star versus its color or spectral class or temperature. Okay, they all mean the same thing basically, and it turns out that there is a very strong correlation here between the temperature and the luminosity. The bluer a star is, the hotter its surface is, the more energy it sends out, right? This is good for 90% or so of the stars. So if you're totally unsure about anything else, then you have a 9 in 10 chance to hit a main sequence star and therefore judge its luminosity correctly. So if you, for instance, find a star that is a white star, you would say roughly that star has, a luminosity of, I don't know, 20 or 30 times the luminosity of the sun. Okay, and then you can go from there. So that means you can judge from the color the luminosity. The luminosity times the or plus the observed brightness gives you the distance. This is called the spectroscopic parallax. Not a very good term because really there's no parallactic effect here at all, right? It's just parallactic effect as in the determination of the distance, right? So that's pretty good, gets you pretty far out because some of these main sequence stars are very luminous, and that means you can see them from very, very far away, right? If you see it's a blue star, then that blue star is so luminous, let's say 10,000 times the luminosity of the sun, that you can see it from very, very far apart. And so that means that takes you pretty far out there into the universe. All right, to go any further, we need even brighter objects, right? And again, I shouldn't say brighter objects, we need more luminous objects. We need something that is sending out even more energy. And for that, we need to go to stars that are abnormal, so to speak, right? So variable stars are stars that towards the ends of their lives. And they would actually, as the name suggests, be variable. So their luminosity will differ over time. And if you can understand what is going on there and you understand what kind of star does something like that, you can again probably judge the energy output of that star, the luminosity, and there you go again, luminosity plus the observation of the brightness of the star in the night sky gives you the distance to that star, right? The stereotypical star, variable star is the Cepheid, which has a light curve, which means, there's a curve, I think I have it somewhere here, that I think there it is. So you have a light curve, meaning you measure the brightness as a function of time, so maybe in days. And so these Cepheids have periods of a couple of days to really, a couple of months or something. And depending on their luminosity, they would actually have a longer pulsation period. So the longer the pulsation period is, the brighter these stars are. And again, I shouldn't say bright, I should say luminous, right? So here's that graph that was found by Henrietta Leavitt in 1908, actually. I have the year here. And as you can see here, the luminosity varies, and this is not linear, this is like a log plot here, varies with the period, and you can see clearly the longer the period, the more luminous the Cepheids are, right? So you measure, the idea is you measure the period, and that gives you the luminosity. Once you have the luminosity, observe how bright it really is, which you anyways did already, the night sky, and that gives you the distance to the Cepheids. Cepheids are very, very bright, and so therefore you can see them from very, very far away. The same thing is true for the so-called RR Lyrae stars. They have the added benefit that they're about 100 times, all of them, regardless of what specific star you're talking about, they're about 100 times as luminous as the sun. And so therefore, again, you have the luminosity, you observe the distance, you observe the brightness, and then you have the distance. Okay, so that was used, for instance, to figure out the distance to another galaxy, the Andromeda Galaxy, which in fact was turned into a galaxy by Edwin Hubble in the 1920s, because the Andromeda Nebula, as it was before known, was found to be a galaxy of its own, because it's so far away that it's must be out of our own galaxy, which we knew had a diameter of about 100,000 light years. And so if you measure a distance of 2 million light years, then clearly this is a galaxy of its own. So that's the variable stars. And as I just said, this was used to figure out that these nebulous spots in the night sky are actually galaxies. Once you know that, and do a little bit of galaxy morphology, meaning you distinguish different types of galaxies, like spiral galaxies, elliptical galaxies. It was used yet again to judge the luminosity, this time of a whole galaxy. How luminous is a galaxy? Well, that depends on its size, right? And how do you get the size if you don't know its distance? The idea is that at least the rotating galaxies, the spiral galaxies, are rotating, and they're rotating faster if they have more mass. But if they have more mass, that means there's more stars, and that means they're brighter, right? They're more luminous. And so you can work this up into a method to look at the spectral lines of the spectrum of such a galaxy. And since part of the galaxy is approaching you as it rotates, and part of it is going away from you, receding, you would actually get a blue shifted signal. You would get a red shifted signal. And of course, the nucleus of the galaxy is not getting closer or farther away from you. So that would be unshifted. If you put all three together, you get actually a pretty wide spectral line, because you can't really separate the three shifted signals or unshifted signals. So you get a width of a spectral line. And so therefore the width of the spectral line gives away the rotational speed of that galaxy, right? So the wider the line, if we follow this thinking, the wider the line, the faster a galaxy rotates. The faster it rotates, the more mass it must have. The more mass it has, the more stars it have. So the more stars it has, the bigger the energy output, the bigger the luminosity of that galaxy, right? So that's known as the Tully-Fisher relation, which was actually something of the 1970s, so very late in the game, where you could judge the luminosity of the galaxy by the width of its spectral lines. If you have the luminosity and you observe how bright it appears in the night sky, you get the distance to the galaxy. So very nice. All right, so finally we're to the last rung of the cosmic distance ladder, which is Hubble's law, something from cosmology, which eventually turned out to be from cosmology. It didn't start this way. And so the finding was by Hubble and actually others before him, but it bears Hubble's name, so I'm just going to use that. Is that if you observe galaxies and you observe these black lines, the so-called Fraunhofer lines or dark lines in the spectrum, then you find that there is a relation between the distance of the galaxy and the shift of these lines. For instance, the hydrogen lines you measure in the lab, and they should be at a specific wavelength or frequency, and you find that they're actually shifted. They're not at this frequency, but they're shifted towards the red. They're actually appearing redder, or in the redder spectrum, in the longer wavelength spectrum. And we know that this is the Doppler shift. That means that this galaxy must be moving away from us. If it sends out light, then that light appears to us to have a longer wavelength, because when it sends out the next crest of this wave, it's already farther away. And so therefore, crest to crest, the wavelength would appear longer if that object is getting away from you. So that's the red shift there. And it turns out that if you also are able to measure the distance of these galaxies, then there is a correlation between the two. And there's actually a very simple law, the so-called Hubble law, that tells you the recessional velocity of the galaxy as a function of its distance. The velocity is in fact some constant called Hubble's constant times the distance, right? Initially, of course, you have to measure both. You have to measure the recessional velocity and the distance to the galaxy to get this Hubble constant. Once you have the Hubble constant, then you can use this as a distance measurement, because the recessional velocity is very easy to measure. I mean, not very easy to measure, but readily measurable by saying, how much redshift do the spectral lines of the galaxy have? And then take this and, you have the velocity, you want the distance. So take the velocity divided by the Hubble constant that has been established from other measurements, and you have the distance to the galaxy, right? So that's very nice. As you might know, the Hubble constant is also very important in cosmology for other reasons, because it is an inverse time, and it is actually the age of the universe, the inverse of the age of the universe, right? So if you take the Hubble constant, about 65 kilometers per second per megaparsec, a little bit weird, but kilometers per second is a velocity, and megaparsec is a distance. So that's 65 kilometers per second faster each megaparsec further out you go, right? For each megaparsec, the galaxy is 65 kilometers per second faster, right? These days, I don't want to go in there. The value is slightly different, right? There's actually a little bit of a tension there between two measurements to measure the Hubble constant. So far it's not going away. There's two different methods, and they give us different values for the Hubble constant. It's pretty exciting right now. But oh well. So in broad terms here, the Hubble constant is the inverse of the age of the universe, because if the galaxies are going farther and farther away, in the past they have been closer and closer together. And if you kind of run this backwards, then you get to the Big Bang, right? All right, so I'm almost at the end here, the latest surprise here is, and again, this latest surprise is really over 20 years old now, is the find that if you look at basically the brightest things that we have in the universe, which are supernova explosions, right? In particular, the type 1A supernovae. You can predict very well how much energy they would release, because you know what this thing is. This is a exploding white dwarf, which is exactly 1.4 solar masses. So you know a lot about this object. Again, you know its luminosity. Same idea here. If you know the luminosity, you observe how bright it appears. Out comes the distance. So two teams in the late 1990s measured the distances to supernovae, and they found that they're actually dimmer than they should be. Okay, dimmer than they can be, in fact, if you assume that the universe is an expanding universe with an expansion rate that is slowing down. right, as it should, because if there's mass in the universe, mass attracts other mass, so it breaks this expansion, right? What else could it be? But what these two teams found is that, well, that's not what we see. What we see is that the universe actually must be something in the universe that is accelerating this expansion rate, and this is now known as dark energy. So some weird stuff, for lack of a better term, that would actually accelerate the expansion of the universe, right? Gravity would slow it down, but we observe that the universe must be expanding faster and faster because these supernovae are farther out than we can otherwise explain. We still don't know what that stuff is, but at least we know it's there. So here's again the idea. If you measure the, here's the basically the magnitude, so the brightness in some sense of these supernovae, and here's the redshift, which is a proxy for the distance of these galaxies. Then they're all above this line here, which is that short dashed line, which says that we have 100% mass in the universe and 0 dark energy. This omega lambda here is the dark energy density, basically, and the omega m is the matter density in the universe. We can't actually explain that these supernovae are so dim, meaning they are so far away, if we assume that the universe is just expanding and slowing down its expansion. We have to assume it is actually speeding up its expansion, and then these supernovae that are, way out here at large distance or large z redshift are so far out that they can only be described with a universe that consists mostly to 3/4 or so out of dark energy, and only 25%, 0.25, are matter. All right, so that basically takes us all the way to the end of the universe. So we've kind of come to as far as we can look. We can actually measure distances, and that yielded a surprise that the universe is actually not acting in the way that we thought it would. Okay. All right, I guess I'm sort of at the end here. Thanks for your attention, and let me know if you have any questions.
Thank you, Uwe. I'll kick off with just maybe a rookie question. This all sounds very scientific and precise. It sounds like we've solved all mysteries about distance in the universe. Is there any boundaries of uncertainty within any of these? Are there ones that seem more like wild-ass guesstimates than precise measurements? Where's the frontier of this right now?
Yeah, very good question. So the basic idea is, of course, the farther out you go, the bigger the uncertainties are, right? So, the way that it works is there is always, of course, an uncertainty, they go back, so astronomers go back regularly and check, right? Even if, let's say, you're making a mistake at the first rung of the ladder, because the first rung informs the second rung, which informs the third rung, and so on. So that could completely throw you off, right? And this has happened a couple of times, right? The big thing is, I don't know what comes to mind there is the Cepheids initially. As it turns out, there's two types of Cepheids, population 1 and population 2, which Hubble didn't know, and so he actually estimated the distance to the Andromeda galaxy wrong by a factor of 2. So 100% error, and then later that was corrected, right? Another one is that absorption was not known, that there's stuff between us and the stars that you can't really see unless you have a good understanding of exactly how that light is dimmed. And then I was like, wait a minute, that looks kind of weird. That star looks kind of weird. It is discolored a little bit if we look closely. So hey, there must be something between us and that star. And so therefore you would judge its color, therefore its temperature, therefore its luminosity, therefore its distance wrong, right? So there's definitely lots and lots of things, sometimes effects that we didn't know about, but certainly all these methods have their problems. Parallax these days, of course, we have these great satellites out there, right? I mean, they measure things to incredible precision. But yeah, I mean, when I grew up, it was still like astronomers like, yeah, you always like more or less, factor 10 or so, Why do stars have different temperatures? Yes, very good question. Of course, what we observe initially is like they do have different temperatures, and then question is why? The idea is there that even for normal stars, it's a function of their mass, right? So mass determines that different stars have different masses. And if they do have different masses, then they do have different gravitational squeezes, right? A star that is 10 times as massive as the sun would actually have to withstand 10 times the force of gravity. Therefore, it must produce more energy, right? The energy is pushing the star outwards. It makes it bigger. Gravity makes it smaller. So there has to be a balance between these two, which is called hydrostatic equilibrium. Fancy term, but it's basically, the balance between these two pressures, gravity inward, and then the thermodynamic gas pressure, heat pressure outward. So that means that due to their mass, the stars have to produce more energy. If they produce more energy, then their surface would be hotter, right? So basically, this temperature of the star tells you it's probably a more massive star, so it will have a bigger energy output. Okay. Now, of course, there's two. If you look into the real physics behind this, or some of the physics behind this, which in some sense is superficial, because the Stefan Boltzmann law tells you about the surface of a thing, anything. It could be a star, could be anything else, a piece of iron. Elements, yes. Also, yeah, okay. I'll get to that in a second. So the size of the star is, of course, also matters, right? If you put a lot of energy out, but your surface is very far away from the core of the star, then the star appears redder, right? So the red giants, for instance, have very low surface temperature, partly not because they don't put out a lot of energy, but because they're so big. So per area, they'll actually put out less energy, and so therefore they look redder. Certain elements account for that. Well, yes and no. So technically, yes, because if you look at the light output of a star very, very carefully, you see that the star puts out not just a continuum of all the colors of the rainbow, basically, but there's a couple of colors missing, right? The dark lines that we mentioned. So technically, yes, if there's different elements in this atmosphere of the star, they would absorb that kind of radiation, and so therefore that could, in principle, change the color of the star a little bit. But actually, it's a teeny tiny effect. So it's mostly driven just by the Stefan Boltzmann law. So basically, by the surface temperature of the star. The hotter it is, the bluer it is, basically. With the weird thing is that between red and blue, these are not the colors of the rainbow. Between red and blue, you would have white, right? White stars are in the middle, not green stars, right? Colors of the rainbow in the middle, you have green. But the way that we observe color, the way that this comes out is actually in this, star colors, which are slightly different than the colors of the rainbow.
How well does the Tully-Fisher relation hold? It seems to me like now that we're aware that galaxies have quite a bit of dark matter, it seems to me like a very luminous galaxy might have a dearth of dark matter, and a very faint galaxy, or a very low stellar population galaxy might have a very high percentage of dark matter. You know, you might have more dark matter than a larger galaxy, for instance. So it seems to me that this would throw off the Tully-Fisher relation quite a bit.
Yeah, I think my understanding is it was always, kind of a, sort of like 25%, something like that. So always had a pretty large uncertainty. So it was kind of good as a, rule of thumb, but it has certainly been modified. So as part of that, we have a better understanding, so we model it better. So, we will revisit our methods of distance measurements.
Another distance measuring tool I don't think that you mentioned was gravitational lensing. If you have a quasar,
Sorry,
you
yeah,
get a
this
really
is
good baseline.
Yeah, okay. So the idea is that there is this general relativity effect that mass can basically bend light, right? Actually, that's a little bit of an oversimplification, of course. But if you have a object between you and a source of light, you can actually see lensed images of that object. Typically, they're like arcs or so. So if you have a pretty bright background galaxy, and then you have a galaxy in the foreground, that galaxy would actually bend like a lens, would bend the light. And so therefore, looking at these images produced, you can judge basically the mass of this, and therefore the luminosity of this this foreground galaxy. Okay.
They often use quasars that are extremely variable in their light output, and then you can measure the time delay between the different images of a lensed quasar, and see how much time difference there is on one side of the galaxy from the other side of the galaxy, and get there's a slight delay in the variability from one side to the other, and then we're able to determine how much longer the light path is on one side than on the other. And since we know the angle between those two, then we can know how long the baseline is given the speed of light. So
Yeah. So it's certainly, that's fascinating too, and what they do there with also microlensing and finding exoplanets, and pretty phenomenal. Sorry, yeah, I didn't get into that at all. And also not sorry, see the chat here, the mnemonic of the HR diagram. Yes, sorry, it is really weird, like, right? O and B and then A, right? So it should be A, B, C, D. But there's a couple of instances where astronomers are just like, okay, that's what we did, and we thought it was okay, and we rearranged it, and so therefore just deal with it. We're not going to change it. All right.
I just wondered on the Hubble constant, why there is still that uncertainty and variation in estimates for the Hubble constant.
Yeah, so there's basically two different ways of measuring the Hubble constant. You could measure it through what I said here, basically. So you measure the redshift of galaxies and the distance of galaxies, and so you get one value this way. Or you could take the cosmic background and the background radiation and do it that way. And so there's a little bit of a tension there between the values that they're getting. One is getting a little bit bigger value than the other one, and they're not quite sure if that is an actual effect. It might be that the Hubble constant is not constant. You're measuring it, earlier in the universe, versus later in the universe, so to speak. I think it's still not quite clear where that comes from.
Okay, thank you.
Any other questions? Okay, I guess we're all set. Thank you very much, Uwe. Outstanding.
Yeah,
Very
sure.
good presentation. Thank you.